Over the next couple of weeks, we're going to be looking at rotational motion, objects that are spinning around in circles or just moving in a circle. And we're going to be looking at some equivalence between linear quantities that we already know about and rotational quantities that are analogous to those linear quantities. So let's say we have an object moving around a circle. It goes along, travels some distance, and winds up here. Okay, this is a circular path, and this is the angle that it's covered. I'll call this a delta theta. Okay, and this is a theta is an angular position, which makes our delta theta angular displacement, meaning that our delta theta, it's analogous to our delta x. I'm going to make a little column here. Rotational quantities, linear quantities. Our theta is like our linear x, or y, I guess, whatever you want to call it. And I'm going to keep this running list of different quantities that we use. Now, if we consider the quantity of an angular displacement per time, a delta theta over t, we call this an angular velocity, omega. This is the Greek letter omega. It's kind of like a curvy W, right? So we've got angular velocity, which, as you might guess, is the equivalent of our just normal velocity. And then I should say this is an omega. Average angular velocity is delta theta over t. And then we can also define angular acceleration. The Greek letter alpha, the little fishy, is delta omega over t. That is angular acceleration. And angular acceleration, of course, is just like our linear acceleration. Now, so these are, the equivalents of some of our kinematic equations. We can also note from our little picture here, if this is the distance an object has traveled, by the arc length formula, that distance is equal to r delta omega. Okay, so there's this relationship that exists between distance and angle. And then if we divide by t a couple times, we can figure out that there's the same relationship, that omega is equal to I did that backwards. Velocity is equal to r omega, the velocity of the object moving in a circle, or like you could say a point on a rotating object. If you had a wheel, a given point would have that speed, or even if it's a disk, a solid object, you can pick out a point, and the velocity would be r omega, and the same relationship exists between acceleration and angular acceleration. And these are for objects moving in circles or for points on a rotating object. These equations hold true. There's another quantity that's important for rotating stuff, and that is the period, which is usually denoted by the variable capital T. Period is T. This period means the time for one rotation or revolution. Right. And if that's the time for one rotation or revolution, well, we know that one rotation or revolution, in one rotation or revolution, a point the distance traveled is going to be 2 pi r, because that's the circumference of a circle, which means that our velocity is 2 pi r over t, and r, by comparison to our v equals r omega, if this is equal to r omega, that means that omega is 2 pi over t, which could be useful. The velocity is 2 pi r over t, omega is 2 pi over t. Either of those equations could be useful if you're given a period and you want to determine a velocity or an angular velocity. And because of these equivalencies up here, we can also rewrite the rotational equivalent of all of our kinematic equations. If I plug in these in for the linear quantities, then the r's will all cancel out, and our rotational equations look basically identical to our non-rotational equations. We can say a delta theta is equal to half omega naught plus omega final times t. We can say 2 alpha delta theta equals omega final squared minus omega naught squared. And we can say that theta final equals theta naught plus omega naught t plus 1/2 alpha t squared. And these three equations are analogous to our equations of linear kinematics, and we can apply them to various rotational problems. And it is also worthwhile to note the relationship to centripetal acceleration. We know centripetal acceleration, we call that v squared over r, but if we substitute in our v equals r omega, this gives us r omega squared over r. So then one factor of r cancels out, and we're left with centripetal acceleration being r omega squared. So that's worth noting as well, that for motion in a circle at constant speed, constant angular velocity, the centripetal acceleration is r omega squared.